To get the most out of this video, you should know and understand the trig ratios and their complementary results. If not, I recommend watching video 10 in this series before continuing, although we begin this video by summarising these results, since the complementary result for tan leads us directly to our reciprocal ratios. We label the sides with respect to angle theta at vertex A. The hypotenuse is C. The side opposite to theta is A, leaving the adjacent side here, labelled B. Completing our ratios, sine is opposite over hypotenuse, which is A over C. The cosine ratio, cos theta, is B over C, and the tangent ratio, tan theta, is A over B. You will also learn in advanced trigonometry topics that these ratios can be defined in terms of the coordinates on a unit circle, as briefly demonstrated here. We will need a basic appreciation of this later in this video. Switching to angle B, which is 90 minus theta, also switches the opposite and adjacent sides, and we can read our complementary results as follows. We see sine of the complement to theta is B over C, the same as cos theta. This gives our first complementary result. Sine of 90 minus theta equals the cosine of theta. And this explains why cosine is so named. It literally means complementary sine. Unsurprisingly, looking at the cosine for 90 minus theta, we see that it equals the sine of theta. Sine and cosine are complementary to each other. The tangent ratio is different. Tan of the complement to theta is the reciprocal of tan theta. However, this reciprocal is also complementary to tan theta, so we introduce the name cotangent to mean complementary tan, or cot for short. Tan and cot are not only complementary to each other, but are also reciprocals of each other. Does this reciprocal relationship also apply to sine and cos? We expect that their reciprocal ratios will be complementary to each other, but not to their own reciprocals. Since the reciprocals come from turning their ratios upside down, then the reciprocal for sine will be hypotenuse over opposite. And for cos, the reciprocal will be hypotenuse over adjacent. You might already see that they are clearly complementary to each other, but let's investigate further with our labelled triangle from before. The reciprocal of sine will be C over A, which is clearly not the same as the cosine of 90 minus theta, which is A over C. It does equal its reciprocal though, as expected. Since sine theta and cos 90 minus theta are the same, then so should be their reciprocals. Similarly, the reciprocal of cos theta is C over B, and again it is clearly not the same as its complement sine 90 minus theta. We have confirmed that although sine and cosine are complementary to each other, they are not reciprocals of each other. So we need new names for their reciprocals. In fact, we only need one new name, since the other will be complementary to it. So we will simply add the prefix co to it, the same way we did for cosine and cotangent. This brings us to a common misconception amongst students and even some teachers. Instead of naming the reciprocal for sine and then using co with it for the reciprocal of cosine, we actually name the reciprocal ratio for cosine instead, meaning the prefix co now belongs to the reciprocal of the sine ratio. Granted, it seems counterintuitive until you know the origin of the name. The name for the reciprocal of cosine is secant, or sec for short. And so the reciprocal of sine must be cosecant, or cosec for short, since the two ratios must be complementary to each other. The origin of the word secant is the Latin secantum, or secare, meaning to cut. In geometry, a secant is a line that cuts a curve in at least two places. You might recall a secant in circle geometry. Notice also a tangent, which is another name used as a trig ratio. To understand why, we need to go back to the fact that the ratios can be defined in terms of a unit circle, as mentioned earlier in this video. The following demonstration only aims to help you appreciate their origins, and as such is only a superficial treatment of the content and concepts involved. Creating a right triangle inside, like this, we see the hypotenuse has a length of 1 unit, which is the radius of the circle. So the y value here and the x value here actually equal the sine and cosine ratios for the angle theta. When you delve further into this, you will be able to define the trig ratios for angles of any magnitude. The reciprocal for the cos ratio would be 1 over this value, verified also by flipping the hypotenuse over the adjacent side, since the hypotenuse has a value of 1. Creating a larger similar triangle here, with theta in exactly the same position, the adjacent side now has a value of 1, being the radius of the circle. So cos theta is also equal to 1 over the length of this secant. Do you see where we're going with this? That's right, the reciprocal of this is the length of the secant over 1, which is simply the length of the secant. The reciprocal of the cos ratio is quite literally the length of the secant, hence the name. I remind you that you don't really need to know this, but I hope it helps you appreciate or at least accept the naming convention. For interest, tan theta will be this length in the larger triangle, and you can see now where it gets its name, being literally a tangent to the unit circle. Perhaps even more interesting is that tan theta is also the same as sine theta divided by cos theta, made obvious in the smaller triangle, since the opposite side here is sine theta and the adjacent side here is cos theta. You could also get this algebraically from our expressions in this triangle or by using the definitions themselves. Using sine over cos becomes a over c all over b over c, or opposite over hypotenuse all over adjacent over hypotenuse. If you understand fractions well, then you know the c's cancel, meaning the hypotenuse has cancelled. Or you might prefer to change the fraction into a division like this, a on c divided by b on c. We can actually divide tops and bottoms since the denominators divide into each other, giving us a over b all over 1. Or you might be more comfortable inverting the second fraction and multiplying. Now it's clear that the c, i.e. the hypotenuse, cancels, confirming the result is a over b, which is the opposite side over the adjacent, the value of tan theta. Returning to our reciprocal ratios, once handheld calculators became commonplace, there was little need for these ratios. Historically, before calculators, the reciprocal ratios were used to make calculations without a calculator easier. Simply put, it was easier to multiply by a reciprocal value obtained from a prepared table of values than to divide by the normal ratio value. Consider the calculation 12.4 divided by tan of 25 without using a calculator. The required values for our trig ratios were obtained from prepared tables of values, similar to this one. Reading across from 25 degrees, we see that the value of tan 25 is 0.4663, correct to 4 decimal places. And next to it, we see its reciprocal, cot of 25, is 2.145. Being the reciprocal ratio, we know that cot 25 is the same as 1 over tan 25. So 12.4 divided by tan 25 can be rewritten as 12.4 times 1 over tan 25, which is 12.4 multiplied by cot 25. It was far easier to calculate 12.4 multiplied by 2.145 without a calculator rather than 12.4 divided by 0.4663. Now that students have easy access to scientific calculators, there is no need to teach the reciprocal ratios for right triangle trigonometry. But, as with the complementary results, they will be important when undertaking higher levels of study.